This video is about lenses. So we're going to switch from mirrors into lenses. Converging lenses. Converging lenses behave like concave mirrors. Light refracts towards the principal axis, so it bends the light towards the center, and it can create real or virtual images, all of which are facts of concave mirrors. And also the focal length is positive, also a fact of concave mirrors. So converging lenses, they look like teardrops. Okay? They have that round curve, fattest in the middle, thinnest on the outside. Okay, so if your fattest point is the middle, you're a converging lens. The other type of lens is diverging. Diverging lenses behave like convex mirrors, and light refracts away from the principal axis. And they also create only virtual images, and their focal lengths are negative. All things that are true about convex mirrors. And diverging lenses, they're thinnest in the center and widest at the top. Okay, so you can see that they're nice and thin there, nice and fat there, and the light hits it and bends away. Sometimes you might hear the words concave lenses and convex lenses rather than mirrors. And this is an example of a concave lens because if you look at it, it's shaped like the concave mirror. Even though it behaves like a convex mirror, it's shaped like a concave. Just in case you ever see that, it really depends a lot on your textbook, on what they decide to use. All right, this is where we switch from mirrors to lenses and where our pictures and our minds need to separate. Virtual images for lenses are on the left side. Real is on the right. So let's think about real. For mirrors, real images were on the left side, right? Because what light really does is it hits it and it comes back. So light truly stays on the left side. But for lenses, if light hits the lens, it's going to go right through it. It's really, truly going to do that. So the real images are where the light really, truly is. So in this case, it really, truly is on the right side. All right, lens diagrams. First one, light goes in parallel, out through or based on the focal point. Okay, just like with mirrors. So in parallel, out through the focal point. Line 2, in through the focal, out parallel. So I go in, excuse me, that's the wrong one. In through the focal point and out parallel. If you look at this, I did 1 and 2 off of different focal points. Okay, line 1 was off of the focal point on the right side, line 2, focal point on the left side. Now, mirrors did not have 2 focal points. Lenses do. The 2 focal points are because light can travel both ways through a mirror, or sorry, excuse me, through a lens. They only travel one way through a mirror. Mirrors only have the 1 focal point because light bounces off and goes there. If I had light going from left to right, we needed a focal point, and from right to left, we needed one. Okay, and we'll see that these 2 focal points are very important, especially with diverging lenses, and makes them flip. You're going to use each of them once. Now, this third line is what's new. And it's new and it's fun. It's not necessarily necessary, but it really kind of does that whole big confirmation. And this line is the easiest of them all. So if you forget how to do one of the others, do this one and the other one. Line goes straight through the center, because if a line hits the center of a lens, it's going to go straight through. So you have it do that. And where the lines meet is your image. All right, now let's get some practice in. This is going to be a diagram for if my object distance is greater than my focal point away. So I have my 2 focal points. And now let's draw. Line 1, in parallel, out through focus. So I go in parallel. Now this is a converging lens. So the line bends towards here, so it's going to bend towards this focal point. And it goes straight through. Line 2, in through the focal point. So I've already taken care of that focal point over there. I'm now going to care about this one. In through focal, out parallel. And now I can already tell you where my image is going to be, but let's confirm. I go in straight through the center, and all 3 lines meet there. I am confirmed. I'm awesome. There's my image. Now, describing the image. The image is really, truly there. The lines really, truly meet. So it's a real image. On the right side, okay, so that's true. It is inverted. They meet below the axis. And as far as larger or smaller, that would depend on how far away you are from the focal point. If I was to take this guy up here, to me, he looks much larger. So he is also larger. There you go. Not too bad. Now, converging lenses also have another state, and that's when the object is closer than the focal point. So let's see what we do there. Line 1, in parallel, out through focus. Nice and easy, and usually the easiest of the bunch. Or maybe second easiest now, since we have that nice third one. All right, line 2, in through focal. Now, I've already dealt with this focal point, so I'm not going to deal with him again. I'm going to look at this one. So if I can't go from my object to the focal, I'm going to go from the focal to the object, keep going until I hit the lens, and then out parallel. So in focal, out parallel. Now those 2 lines don't meet. Let's give it a third and see, did I screw up somewhere? Maybe 2 of these lines meet. Nope. None of these lines will meet. All right, what does that mean? Well, that means that my image must be virtual. So I get to backtrack. So backtrack the refraction. Just like we backtrack the reflection, we backtrack the refraction. And they meet there. Okay, so it's on the left side of the mirror where the light doesn't meet. So it is virtual. It is upright. They meet above the line, or appear to meet above the line. And it is larger. Now, if I was little old me, and I was standing here with my eyeball, looking at this, what I would see if I was right here is the image. I wouldn't see the object. The image is what my eyes would perceive. And that's how a magnifying glass works. A magnifying glass works because your eyes perceive the image, and the image is larger, and it's closer to you than the object, so it overlaps it. So there is a magnifying glass. All right, so diverging lenses, also sometimes known as concave lenses, depending on your textbook, are very diverging. They're diverting. We don't like them. Their focal points are negative, or maybe we love them because, you know, everyone's unique. And so are they. All right, so let's see how this changes things. Line 1, in parallel. Now, out through focus. We cannot do that. No, that cannot happen. Why? Because diverging lenses make the light diverge away. So you know it's going to bend away from the axis. But how? At what angle? It's important. It's going to bend based off of this focal point, okay, which is the opposite one that you cared about with line 1 for converging. You can think about it, negative focal points, they switch. It's the opposite of what you would expect, something like that. So it's going to bend away based off of that guy. Okay? Line 2, in through focal. Now, if it was a converging lens, it would go through the focal point there, right? But it's not, so it won't. We already took care of that focal point. That focal point's all used up. He's tired. We're going to use this one. So we're going to go in through the focal, or based on the focal, as if we could hit it, just like we do for convex mirrors. Ooh, that's a little steeper than it needs to be. Better. Not great, but better. All right, so in through focal and out parallel. And then line 3, straight through the center. Whee! Okay, these 3 lines never meet, and it is a diverging lens. So we know it's going to be virtual. Both those things are true. So we follow refractions backwards. And they meet right there. So the light doesn't really meet, the dotted lines meet. So it is going to be virtual. If it is virtual, it's upright. It is also, by very appearance, upright. And smaller. And every diverging lens will look exactly like this. So they are unique from converging lenses. They are, however, not unique from themselves. Okay? Now, lens diagrams, they changed a little bit. Equations, not so much. We still have 1 over di plus 1 over do equals 1 over f. And our magnification is equal to hi-ho and negative dido. All right, as far as the math goes, the image is still real if di is positive. Okay? Now, if your di is positive, that means that your magnification is negative. So, real images are inverted. That also means that your hi is negative. Both those things are true. They're just different ways of seeing it depending on what you know. Okay? Virtual images have negative DIs, which means they have positive magnifications and positive HIs. Larger or smaller, if the absolute value or the positive value of n is greater than 1, it's larger. Less than 1, it's 0. Or sorry, it's smaller. And if it's equal to 1, it's the same size. Okay, so your numbers, they don't change very much or at all. Where positive and where negative is does change. All right, so let's see. Let's do this one more time. I chose a diverging lens because, well, it's probably the trickiest and the one we're most likely to screw up. So if you're ever given a situation and you just have to describe it, you can do whichever makes you happy. Whether you like the math or the picture, they'll both work. So I'm going to take the words, throw it into the picture, and then we're going to do both ways. And you know, you're responsible for being able to do both ways, but sometimes you get that choice, and it's nice. All right, so we're going to find the DI and the magnification when an object is 1.2 meters from the lens and has a focal length of 0.5. All right, so if f is 0.5, 2f is 1, so we're going to be farther away than that. So I'm just going to throw us up here. All right, so line 1, in through focal, or sorry, in parallel, out through focal. In parallel, out through focal. Line 2, in through focal, but not this one, this one. In through focal, out parallel. Now it's a diverging lens, so I already know that I'm going to have to backtrack. So I could already tell you where my image is located. Well, let's do line number 3. Straight through the center. There we go. All 3 lines meet here. So if I wanted to describe the situation, I would say it is virtual, upright, and smaller. That's what the diagram shows. Now let's do it with the math. I know that my DO is 1.2. And I know my F is 0.5. But I also know one more thing. It is a diverging lens, which means my F is negative 0.5. Keep that in mind, because if you screw that up, you're like, oh, and then no. All right. So if I'm solving for DI, 1 over DI plus 1 over DO equals 1 over F. So 1 over DI plus 1 over 1.2 equals 1 over negative 0.5. So 1 over DI is equal to negative 1 over 0.5 minus 1 over 1.2. And if you want to find common denominators, you can. My recommendation would be, I believe that 6 is the smallest one. Or you can use your calculator. Make sure you keep that negative in mind, though. And I get 1 over DI is equal to negative 2.83. But that's not where I'm done yet. I need to cross multiply, right? Or get DI on top, flip it, however you want to do it. And we get 1 is equal to DI, because 1 times 1 is equal to DI times negative 2.83. Divide by negative 2.83. And I get DI is equal to negative 0.353. Now that's my DI. If I want my magnification, M is equal to negative DIDO. So M is equal to negative 0.353 divided by 1.2. And that would be a negative of a negative. So might I point out that we also have that negative. So they work out to be positive, and works out to be M is equal to 0.294. All right, so let's see if we can't describe. DI is negative. DI is negative. It's a virtual image. Now magnification is positive, so it's upright. It's also upright because DI is negative, and if it's virtual, it is upright. And magnification less than 1, so it is smaller. And if you look, both things are described the same. So it all works out beautifully. All right, that's it for the lesson. Good luck on your homework.